Now that I have two good oscillators, this Wenzel and this one that I built myself, I run them through low noise amplifiers, means low flicker noise, and also these ones, to get plus 26 dBm to send into my mixers for my 2-channel receiver. It should be possible to measure sideband noise at very close range. I have placed the oscillators here where they are isolated mechanically by this very heavy piece of iron, and there is foam plastic beneath it. They are supplied with power from separate, well-filtered DC supplies. So hopefully there isn't any correlated noise at low frequencies between those two units. They have their separate amplifiers for the Wenzel 12 dB and for this oscillator 10 dB. As a first test, I look at this oscillator from CMAC, and this is what I see. The frequency separation is small, only 20 Hertz. So I have the signal and the mirror image. But at the close range, here I see the noise of this crystal oscillator, and it's very good. Minus 128 at 5 Hertz, and at 10 Hertz maybe minus 138 or so. Here is the frequency drift after I switched on my own unit. It drifts upwards in frequency, and here it stays. And here is the same with more magnification. So I can see a single Hertz from here to here. Now I know that this unit has some frequency drift. Probably I should make it a little bit warmer. The temperature now is 63.1 degrees. There is an immediate frequency jump when I change the supply voltage. By changing the temperature, causing the thermostat to use more power. So the first thing I have to do with this unit is to supply the thermostat from a separate voltage source. And I can also see that now the temperature is far too high. And that is 69.7 degrees. I have been collecting data for about 5 hours now. And what I see is at 1 Hertz, this line, minus 120, and 2 Hertz here, minus 131. The signal here is separated from the mirror image by something like 30 Hertz. So what I see here is the signal itself, its carrier. Here at 15 Hertz, it is the second harmonic and the zero frequency spur down here, which is essentially noise, I think, but maybe some DC component. And then here it is the mirror image together with the third overtone. And we can see the noise of the direct conversion receiver is high because I am so close to zero. And at higher frequencies, of course, the noise goes down. So I am losing something like 15 dB because I'm too close to the center frequency. But with my previous system, the sideband noise of my local oscillators were much worse. So I can use this for close range measurement, and I have got successfully results when measuring on this oscillator. And I will now change the way the thermostat is supplied with DC power. To see what happens at 5 Hz and above, I will decrease the transform size. So I go from N17 16 times. That is 13. And I have to expand the scale a little bit to see better. And I want to see what happens at 5 Hz and above. The improvement I've seen is not only because I disconnected the thermostat and the noise that comes from it, I also changed the way I'm doing the measurement. Previously I injected the signal here, cut this line and inject the signal with an attenuator here. Now I'm injecting the signal directly on the hybrid, and I put attenuators here to set the signal level at an optimum place with only 1 dB margin to the saturation of AD converters. And which one of the two makes the biggest difference, I don't know, and I don't want to take the trouble to find out. What I have seen so far is very promising. It's these points, and they fall on a perfect straight line below everything that I have seen published before. With a much smaller transform size, I have collected 35,000 almost averages in only 5.5 hours. And now I can see the noise at a separation of 10 Hz. The curve is still a little bit noisy, but the mouse is placed where I can estimate within less than 1 dB, minus 156 dB per Hertz. I have left Windows 7 and booted into Windows XP, the 32-bit version. Here I have proper drive routines for the Delta 44 sound card, and I have switched from the UADC4 to the Delta 44 because this center peak seems to be more favorable. The noise floor is probably 1 decibel or maybe 2 decibels lower now, and I have run for 15 hours, and I can read the noise at some frequencies. 6 Hz minus 150, 10 Hz minus 156 or maybe 55. The curve is a little bit unstable because the imaginary part is pretty close. And 15 Hz, I cannot say well, but maybe minus 160 here. I have now connected the thermostat, and that has caused the frequency to go up a bit, so the noise level is now higher because I'm closer to zero frequency. The noise floor is, I think, about 4 decibels higher. But I still can do the measurement reasonably fast. This is 3.5 hours. And at 1 Hertz, minus 122, 2 Hertz, minus 132, and 3 Hertz, minus 138. And then the values start to become a bit uncertain. The higher temperature has clearly degraded the sideband noise performance. These red dots are what I just saw, and that's about 3 decibels degraded compared to these blue dots that I measured at room temperature. So 40 degrees more temperature has degraded sideband noise by 3 decibels. And it's no longer better than the best published. It's the other way around, but the differences are very small. I have disconnected the cable for phase locking, so this oscillator runs independently from the Wenzel oscillator now, and I turned the frequency adjustment knob here to make the frequency difference about 0.5 Hertz. And this one, the oscillator with the J-FETs, is the signal source. And here is what I see. The two signals are pretty close to straight lines, but not perfectly. The variations when these two vary the same way, the correlated frequency adjustments we see, that is because of my J-FET oscillator frequency instability. The noise we can see on the sides here, this is the Wenzel oscillator, and this is my homemade oscillator with bipolar transistors. And the bipolar are clearly far more stable when it comes to sideband noise. And it also looks like there are not so many correlated frequency shifts. It means that the J-FET is fairly stable. And it looks like this one is a little bit straighter than this one. And this is the Wenzel. I changed the color scale to see the sideband noise more clearly. And it's very obvious now that here the Wenzel oscillator has much more noise than the bipolar oscillator. And of course, on this, the noise I see is the sum of the noise of the two oscillators. And the noise, the big difference I can see is at the frequency separation of about 0.1 Hertz. Sorry, 0.01 Hertz. Here is the decimal 6, here is the decimal 0.7, and it's still 0.7, and here is 0.8, so it is 0.01, 0.02, 0.03. So from here to here is 0.5 Hertz. So I couldn't see this well in the phase noise measurement because this is very close to the carrier. When the J-FET unit is tuned for the lowest frequency, maximum capacitance, Q is 1.23 million and the gain 1.16 dB. Now I have retuned it for the highest frequency, and here the Q is 1.24 million and the gain 6.8 decibels. In both cases I have the thermostat running and I will switch it off. Now I have switched off the thermostat and this is the highest frequency for the unit. Q 1.25 million and 6.79 dB gain. And here is the lowest frequency without the thermostat. 1.24 million for the Q and 1 dB gain. Now these two units are the local oscillators, and the unit from Wenzel is the device under test. What I see is not quite expected. The red trace is the oscillator with bipolars. The blue is the oscillators with junction FETs, J310, and the yellow is the correlation spectrum. And it's clear that the noise, the correlation spectrum and the bipolar are very similar. Means that the red trace is dominated by the noise from the Wenzel, but the blue trace is high above, 2, 4, 6, 8 decibels or so, at 1.5 hertz. At half a hertz, the thing is more uncertain. Probably there is something with the bandwidth of the filter I'm using here. It's not narrow enough. So there is a component that is out of phase. I have swapped the cables between the two oscillators, and the red and the blue trace have changed places. So the problem is the oscillator and not anything else in the received channels. There could be flicker noise from 4 connections in the B and C connectors or something else. But it is the oscillators. I have made the frequency lower of the 2-channel receiver. That degrades the noise floor, and I can see the center noise here coming up. But the difference between the blue and the red curve is smaller, means noise has been reduced when power is reduced and gain is reduced of the FET amplifier. Then I swapped the power supplies, and this is the result. One channel is degraded. The red is now clearly above the yellow, while it was not here. But the blue is the same as the red. So I have to do something about the power supplies, and obviously both channels are affected of it. I don't have at all as good filters on the DC supplies as I had when running with these oscillators as the device under test. 1 hertz here. I have replaced the noisy power supply and also added RC filters, 8 ohms, 0.1 farad on the DC power supplies. That is far from the filter I used when using these as devices under test, but it has solved the problem of one oscillator being more noisy than the other. Although maybe not at very close range, 0.1 hertz or so, and that is of course not filtered by the time constant I added, the RC, but down to 1 hertz I can see that the noise is maybe 2 decibels above the noise of the Wenzel oscillator itself that comes from the correlation measurement. It means that this contains the noise of the Wenzel plus the noise of the oscillators. So they are significantly below the Wenzel oscillator. But they are not 0, because then they would be on the same level as the Wenzel oscillator. And then when I come to 3 hertz, I am into the flat, because the noise floor is very high, because I am very close to the frequency of the device under test. So I have the 0 frequency, the 1/f noise of the sound card. I will try to move the oscillator frequency away, upwards, to see whether I still have a low noise. Now the 2-channel receiver is running at the highest possible frequency, while the Wenzel is running at its lowest possible frequency. Means I have a frequency separation of about 70 Hertz, maybe 75. And that places the noise significantly away from the interesting region where I'm doing measurements. And you can see the noise floor on the both sides, how it differs. Anyway, here is the noise floor now, about minus 135 dBc per Hertz. And it has been running nearly 9 hours, so I have good statistics. And I can see the noise of the Wenzel oscillator at minus 119 dBc per Hertz at 1 Hertz. To get the value at 10 Hertz, I compress the scale and I can read here, minus 147. And above 15 Hertz I cannot evaluate with this setup. Maybe if I wait some more time, but that's going to be a little bit uncertain. I have plotted the noise levels that I have seen now for the Wenzel oscillator. It is these points. They fall on a perfectly straight line, and they fit reasonably well to my very old measurement here. At this time I could not go closer than about 10 Hertz. So the truth is probably a little bit below, but joining the measurement at higher frequency separations. So this is what I can say now. What I have is limited in performance. I cannot go far away from the center frequency anymore. Previously, with the other oscillators, I could not go close. And this is, of course, I would need an oscillator at a larger separation from 10 megahertz. But that's not so easy. Here is the amplitude noise. It's much lower. At 1 Hertz, about minus 139.5. And it seems I can measure as close as 0.3 Hertz, or maybe even closer than that. But with some question mark, because the imaginary part here is pretty close. Anyway, this system is now satisfactory from many points of view. I will see what I can use it for in the next video. With an expanded scale, there is 0.2 Hertz here. I can see a significant difference between the bipolar transistors, the red trace, and the field effect transistors, the blue trace. And at this low frequency, the low pass filter I have on the supply voltage is no longer making a good filter. So the sensitivity to voltage variations, which is much larger for the JFETs, is visible here. But at 1 Hertz here, the amplifiers are very similar, because the noise is determined by the crystal itself and not by the amplifiers. I think so, at least. I can also see in the baseband graph that there is more noise on the green trace than on the red, at a frequency separation of about 0.1 Hertz.